Hi everyone, in this video we're going to talk about homoscedasticity. The first question is, why is homoscedasticity important? And so let's recall the purpose of this channel is to help the audience learn all about hedge funds. In this video we'll teach you about one of the critical assumptions of an OLS regression, and that is homoscedasticity. This is for educational purposes only and is not investment advice. By the end of this video you will have a basic understanding of homoscedasticity, which will help you better understand the OLS regressions that are run in the finance literature, and then hopefully after more videos and more work, run your own finance research, and specifically which type of regressions to use and when. Watch the video until the end to make sure you have a rock solid understanding of homoscedasticity, so you know it later for your academic and professional career. And two, there will be a short quiz at the end. Please feel free to post comments with any questions or any topics you would like to see covered, and don't forget to smash the like button. Homoscedasticity, recall the capital asset pricing model and what it took to come up with Coca-Cola's expected returns, right? Coca-Cola's return equals alpha plus beta times the market return in any given period plus epsilon t, which is the error term. Homoscedasticity is the assumption that the variance of the error term, conditional upon xt, which is the market return, is constant across time. In particular, you see this variance of epsilon t given xt equals sigma squared. So basically it's a constant, right? So this, if we were to annotate this, we could imagine that the error terms are basically constant over time, or the variance of the error terms are constant over time. And that's what we're going for with homoscedasticity. And again, the reason this is important is because this is one of the central assumptions of the OLS regression. And so we want to make sure that when you're using the data, whatever data you're using, if you're going to run an OLS regression, that your error terms are homoscedastic. Okay, can we think of reasons error terms would not be homoscedastic? Well, xt in this example represents the market returns. If we had omitted variable bias, is there another explanatory variable beyond market returns that could explain Coca-Cola's returns? And if so, that explanatory variable would be built in to the error term and potentially cause the variance of the error term not to be constant in time. And so you can see this, like, if there's an omitted variable here, right, then the omitted variable is effectively built into epsilon t. Right, I write them as distinct here, but really it would be built into epsilon t. And if it's built into epsilon t, and yet this omitted variable does help explain Coca-Cola's returns, then of course this is going to vary over time, right? And similarly, the variance of the omitted variable of t is gonna vary over time, right? And so when that happens, it's not the variance of the omitted variable t and epsilon t altogether will not be constant, but it will vary. Okay, that variance, and so it's not going to be constant, and so that will cause the error term to be heteroscedastic, which means sort of different, right? Not homo, which is the same. And so can we think of like what would be an omitted variable that would drive Coca-Cola's returns beyond the market? Right? One could be that it's a large cap stock, right? So the size of the firm could be one thing that would predict its returns. Another thing would be the profitability, maybe would help explain Coca-Cola's returns. Another would be maybe legislation, right? How favorable governments worldwide are to these soft drink companies, right? That would definitely affect Coca-Cola's returns, and not be completely contained within the market variable. And so as you can see, and these things might change over time, right? You could imagine that the variance of the legislation would change over time, right? Sometimes governments are very friendly to Coca-Cola, sometimes they're less friendly. This variance of that explanatory variable would not be constant in time, right? We can think even in our own lives, like sometimes, New York State or New York City, allowed Coca-Cola in the city, and sometimes they didn't. So the variance would change depending on the time. Okay, so how to test for homoscedasticity? There are 3 tests that can be used. The first is the Broch-Pagan test. The second is Cook-Weisberg. Third is the White General test. If you see the video on serial correlation that we did for instructions, it'll show you how to run a Broch-Pagan test in Python. What should you do if your data is not homoscedastic? So there are effectively two options. The first is to transform the data by adding a new variable to make sure your model is well specified and reduce the chance of an omitted variable. The second option is to add a heteroscedasticity consistent covariance matrix. Okay, those are effectively the two options. Um, and so that those are effectively your two options in terms of transform the data or add a heteroscedasticity consistent covariance matrix. And then also, you could also use a regression method that accounts for heteroscedasticity, right? OLS does not. And so if your data is heteroscedastic, which you will figure out from a Broach-Pagan test or either of those two additional tests, then what you want to do is either transform the data or add a heteroscedasticity consistent covariance matrix, or use a regression method that accounts for heteroscedasticity, like the weighted regression. Pop quiz. What is the definition of homoscedasticity? Can anyone remember? The variance of the error terms conditional upon the explanatory variable is constant, right? Variance of the error term conditional upon the explanatory variable xt is constant, right? Or equal to sigma squared, which is a constant. All right, so that wraps up the homoscedasticity video. I hope you found this helpful. And yeah, if you have homoscedastic data, be careful of running OLS regressions. See you in the next video.